Hi, we worked on optimization of the knapsack problem this semester. First, let's see what our problem statement is. Let's assume we have a knapsack and we filled it with boxes. Each box has a weight and a value. And the objective is to fill the knapsack with the most value without going over the specified weight limit. Now, this problem can be solved in many ways, but we chose to use the genetic algorithm. In this algorithm, we represent each possibility of selecting a combination of boxes using ones and zeros, which we call individual representations, for a maximum knapsack weight of 15 kilograms. Now, with these representations as our inputs, for a total of 128 boxes, we computed the solution to this problem. Now, genetic algorithm has three parts to it: selection, crossover, and mutation. The first step in selection is calculating the fitnesses of each of these representations.
For fitness calculation, the inputs are individual representations, weight and value array, and we want to calculate the total weight and total value of each representation. And the independent operation here is FMA. We choose SIMD FMA, load, and broadcast as our main instructions here. Each time we will load one bit from 4 continuous representations and do a FMA with the broadcasted value and get a temporary sum, and we'll update the temporary sum in each loop. And we used following strategies to further optimize our code. Firstly, when we compare the total weight with a threshold, we will broadcast that threshold and use SIMD compare and AND operation, which is faster. And secondly, since the value we load are from 4 continuous representations, to optimize the cache usage, we change the matrix to a column major order, which is faster. Thirdly, in our last iteration, we are using too many registers, so this time we refactored our code and limited to 16 SIMD registers. And moreover, we have OpenMP parallelism for this kernel. And because in our previous version, the inner loop will lead to many threads updating the same data. So we have two options. Option 1 is to use OpenMP section to maintain the correctness of our kernel. And option 2 is to do a loop interchange, which can remove the dependencies between each thread, but it will lead to duplicate broadcast. And we implement both and chose the second one according to our experiment results. And here is our performance plot. From this plot, we can see we reached 8 times acceleration compared to our baseline.
Tournaments happen between any two representations selected from the lot, like the one shown here. The representation with a cumulative value of 6 won the tournament. This is our baseline, and it compared only 4 contenders and shuffled the population inside the selection kernel. So, in our initial design, we fetched the fitnesses from only 8 randomly selected representations and kept comparing them until we ended up with 4 winners. We removed the shuffling part out of the kernel but added the fitness computation in it instead during our initial draft. We quickly realized that it was a bad idea and the kernel needs to be split. We broadcasted the maximum knapsack weight onto registers. Even though a good idea, we failed to see that we were doing that for more than 16 registers, essentially losing out on the efficient memory usage. Our kernel is much more optimized now. We not only took in a lot of arguments which we felt are best computed outside its scope, but also were able to efficiently use the registers. We made the number of contenders participating in the tournament dynamic. Also, one major change is that we increased the population size in the later stages of the project to 128 inputs. In this version, 2 sets of contenders are loaded from the fitness array. 4 representations are then extracted to get compared. We also used OpenMP for parallelizing our kernel with 8 threads. Key lessons to summarize were about interleaving instructions and reusing registers. Another key decision we took was to convert our fitness arrays to a column major matrix. This was to facilitate the first bits of all representations to get FM made with the first item's weight or value. The graph indicates the performance plots between our baseline and our current optimized execution.
The crossover operation means to exchange some part between two parents' individual representation, and here we use SIMD permute to achieve that. From the code you can see first we load a pair of parents and then we do permute and then load and store them back. And for parallelism, because each pair is independent, so we can simply use OpenMP Pragma 4 to achieve that. From the performance plot, we can see crossover achieves 16 times speed up compared with our baseline. And here are some lessons learned from crossover and fitness kernels. The first one is to interleave the instructions. For example, in crossover, the store and the load instructions are the bottleneck because we have many of them, and we try to interleave them and hide the latency, which is very important to our performance. And the second one is memory layout have both benefit and cost, because we found that transforming between different memory layout costs a lot when data size is relatively small. And the third one is we need to be cautious about the number of processors to choose when we do parallelism, because we do find when we keep increasing the number of processors, the improvement in our performance is not that significant. And the last one is we need to pay attention to every simple detail, like should we use setPD or load, or is there some duplicate or unnecessary code in our kernel? Both of them will maybe have very big impact on our overall performance.
Is the mutation kernel. So for the mutation kernel, we get the mutation rate based on which the bits of the children are flipped. So for each individual bit, a random number is generated and compared with the mutation rate, based on which the flipped number is the bit is flipped. So for the design phase itself, we choose the dependent instructions, being the compare value of the random and the flipping of the bit, and considering additional factors of SIMD size of 4 and the availability of 16 registers, we have identified the following as the SIMD instructions for the design, and the right side table will have the interleaving of the code instructions as well, based on all of these factors of maximizing registers usage and also adding parallelization with OpenMP parallel for directive. We have this final code for the mutation kernel. Several learnings of this is like previously it had random numbers generated within with a lot of mod operations. So taking it outside of this kernel itself helped improve the performance. Comparing it with the baseline, it's a significant improvement, and you can see this plot over the increasing number of generations and the execution time. So the mutation kernel's performance plot, like the execution time is the elapsed time. So this is the plot over the population size and number of generations. And since there were still too many loads and stores in the mutation kernel, there was a need for a fused kernel because the output of the crossover operation was the input of the mutation operation. So identifying these dependent instructions and designing that kernel, I came up with this fused kernel code again, or adding on to the crossover kernel itself, adding the components of the mutation rate and the compare values for the mutation rate. Add the instructions of XOR and store of those particular functions to each of these compare if statements, and you have the final fused code. The fused kernel has this as the performance plot and has significantly improved over the mutation and crossover that was previously implemented. And there are several lessons learned as part of this project. For me, especially like previously mentioned about changing the place where certain variables are created, reusing registers as much as possible, and interleaving of these instructions as well has improved performance significantly. To conclude, we have successfully improved and optimized performance of the baseline on all three aspects of this algorithm, and we've used design concepts as learned from the course using SIMD operations and theoretical peak and performance measures to understand the actual performance of our optimization algorithms, and also learned that parallelization comes with a cost, because we did find with increasing number of threads and lower generations was increasing the execution time variedly. So thank you for the opportunity, Professor.